So welcome for another training session, guys. I see your camera there. You got everything set up, and that's great. So just I'm gonna share my screen here really quickly, just to kind of brief over the overview, and then we'll get right into it. So I'm just going to give you guys kind of a high-level overview of the AVRS architecture. I think some of you know a lot of this already. It's very similar to the Q car. So is everybody on this call and going to be viewing the recordings? Have they all went through the Q car training?
Yeah, almost all the students and faculty, they were in the Q car as well. Uh, Q
Okay.
car, if
So
I'm
I
not
mean,
mistaken.
AVRS has a very has a similar architecture, right? There's a few, but yeah, we'll talk about that. But the hardware is of course different. So we'll talk about the hardware of the Q Drone 2, I believe you have. Um, about talk about the OptiTrack, the ground station, because there are some differences. Because the Q car obviously did not have the localization system, the external localization. We'll talk about basically how the systems communicate to each other. This you're already quite familiar with, right? So deploying models to local or remote targets. It's a little bit different because for the Q car, you'll notice that sometimes you're running both one on the local and one on the remote and doing kind of a client server type application, right? So that is something that's a bit new. I think we can also show you maybe some more, if we have time, I'll talk about Core Target Manager and Core Console. That can be helpful for you guys to understand a bit more about the inner workings of Quark and to see what models are loaded on the Q car, but that does not take a lot of time. When we're doing the Q drone, we'll do a basic IO test just to get you guys used to having a server running on, like a mission server running on the ground station BC, and another client or controller running on the drone. But we'll just do it as a very simple example first. So that'll be the first example we run. Then we'll go through the QDrone and Quark interfacing. So we'll take a deeper dive into what the core target libraries are, how initialize blocks, and then we'll go through some of the like hardware checks, right? So we'll go through a camera check and a QDrone 2 IO check. After that, I'm hoping to look at all the frames of references. So we will basically, you'll get to define a rigid body in your workspace. And so yeah, we'll do that. So we'll define the Q drone 2, a single object. I'll show you how to do the camera calibration, define how to define the axes, how to define the rigid body. And then when you do all those three things, after you do the camera calibration, after you do the rigid body, and after you define your object, then you can load all that inside a Simic model through the Quark blocks. And then you can basically track the information, right? So this whole localization OptiTrack camera system is meant to basically get the X, Y, Z pitch, roll, yaw position of your objects, right? So whether that's a drone, and I think you got a Qbot 3 there. I thought you only had one Q drone 2, so this is a bit new. You have 6 cameras, so we'll see what we can do. But yeah, we'll go through as much as possible. So yeah, we'll see. That's probably going to be the first session. If we have time, then we'll try running the hover test with the drone only. So if we have time to do that, we'll do the hover test, and after that, we'll do more complex applications like position control and stuff like that. So at least we could start getting to the hover test today. If not, we'll do it tomorrow. Are there any questions about the plan for today? Okay. Okay, so if you agree with this, then let's
Okay.
get into it. Pardon?
Hi, Mitch.
Yeah,
Your mic is muted.
my mic is muted.
It's not muted, but we cannot hear you.
Is it for us as
Um, can you hear me now? Test, test, test. It says my microphone is working.
Yeah, now it's working.
now? It's okay. For 5 minutes we didn't hear you.
Okay, did you hear me when I was going through the agenda?
Yeah, yeah.
Yeah, it was okay. Alas,
Okay.
we can.
Okay, so here is okay, so let's go through this. So this is kind of a mess. I don't know what went on here, sorry. Yeah, so here is basically the structure of the AVRS, right? So you have your ground station PC, and you have your router there. You have a Qbot 3, a Qdrone 2, or Qdrone 1s. It could be a collection. All can be used together as well. Then you have your OptiTrack cameras up ahead, right? So again, the OptiTrack cameras are used for localization, and they're used to get the XYZ position and then even pitch roll yaw of the rigid bodies that you define in the space, right? Your battery chargers are supplied with all these systems. Question, did you charge the batteries?
Yeah, yeah, it's charged.
Okay. The other thing to remember is for these OptiTrack cameras, it's important that before you do calibration, before you do anything with these localization, to turn the cameras on for at least 15 minutes.
The cameras are on. You means opening the software as well?
That's correct. Yeah. So the cameras go on, and you know that because the LED goes on the camera, and
Yeah, yeah.
you do that by opening the motive software.
More. Okay. More.
So it'd be a good idea to maybe open that now.
Yeah.
And by the time we get into the rigid body, it'll be warmed up.
It's open now. Okay.
Excellent. So now you should see all the cameras being having an ID, and the LED should have every camera should have an ID number.
Yeah.
Okay, great. And okay, so as you know, you have a protective netting as well. There's also safety goggles provided. So always be mindful that these are very powerful devices. So when you're using these, please just keep that in mind. I'm talking specifically about the drones, right? So always be mindful of that. So how does this basically work? So you have your core host, and you can run controllers at 1 kilohertz or faster. Um, that is running MATLAB Simulink and Quark. Your localization system is connected through the OptiHub, probably via USB. I think you guys, or you might have another type, but I believe you have the Flex 3 cameras, right?
Yeah.
Okay, so you have 6 Flex 3 cameras and they're connected to the OptiHub. That's connected to your computer. So the computer gets the information from your camera to get the rigid body information. Your computer is connected to the router, just like the Q car. So the Q car, much like the Q car, and so the Q Drone 2, the Qbot 3, Q cars, all these systems are made to log on to the router Wi-Fi, right? So the router broadcasts a Quanser UVS Wi-Fi signal, and all these devices are pre-configured to log on to that. So once that is logged on, you do the ping test, and basically the host and these devices are all on the same network. So that allows you to download core controllers and stuff like that. Um, and You're able to monitor the signals. You're able to change commands. So there's different configurations as well. You'll see that for Flex 3 or Flex 13, if you have 6 cameras, then you'll have a single OptiHub. But if you're using multiple cameras, like the other lab that in the other department, then you'll have multiple OptiHubs, right, with a sync cable. And then you'll see all these devices in Motive. So like I said, basically you're receiving the XYZ pitch roll yaw or the pose, right? The pose of the different objects from the rigid body. And what you want to get used to is when you're doing flight control, the drone has its own, the drone basically runs a stabilizer, a flight controller, and the host has a ground station PC. The ground station will send like the desired position commands, right, to the drone. That's evident. But the other thing to keep in mind of is we're also sending the position of the drone that we get from the cameras. So we're sending that to the drone as well, because the drone is not connected to the cameras, right? So it can use its onboard IMU to estimate where it is in space, but ultimately the direct measurement is being measured from the ground station PC. So they're taking that information and sending that to the drone. Any questions about that? Does that make sense?
Yeah, makes sense. Clear.
Excellent. Okay, let's talk about the hardware a bit. So you only have the QDrone 2 there, right?
Yeah.
Okay, so we'll talk specifically about the QDrone 2. The QDrone 1 is a bit different, but the QDrone 2 is our next gen. So it has an NVIDIA Jetson Xavier processor. It has the Intel RealSense camera, the same one that's used, I think, on the Q car. So it has the Intel RealSense RGBD camera. It has an OmniVision, a downward-facing camera that can be used for optical flow. Again, custom-made impact-resistant carbon fiber frame, just like the QDrone 1, but the QDrone 2 is larger. We have 3 RGB CSI cameras, serial cameras, that are in the rear, left, and right. So you have a total of 4 cameras and 1 underneath, so 5 cameras. You also have an expandable I/O. So you have an expandable I/O with the following inputs and outputs. You have a PWM output, you have SPI, UART, I2C, and ADC, and encoder input. So you can mount stuff on here if you wanted. So yeah, here's a bit more information about how that board looks like, and kind of showing you the top DAC that is on the QDrone 2. So the Xavier is it's a very, very powerful computer, right? 6-core NVIDIA ARM processor. So it's so you have a very powerful computer on the QDrone 2. So we did a slight upgrade from the QDrone 1 there. Here are the 3 different types of cameras that we have. So we have the Sony CSI cameras. We have the OmniVision that's facing down, and the Intel RealSense. So each one has different I guess advantages and stuff. So I mean, Intel RealSense is an RGB in depth camera, has a 3-meter range. The OmniVision is primarily used for, like I said, for optical flow, but it has the highest. It can have a very high frame rate. So you can go 120 by 800 resolution at 120 frames per second, or you can go a lower resolution at 180 frames per second. So it's quite fast, and that can be used to tell the position of the area of the vehicle with respect to an object on the ground, or like kind of the XY position of the drone you can sense from there. A couple of things here is just much like you're used to now with the Q car is you have a power switch, and when the QDrone 2 logs on the Quanser UVS, it will be assigning an IP address, and that will be displayed on the LCD screen. It also shows the battery level, so exactly like the Q car. The one thing that's different here is the flight controllers on on the props, right? So the propellers each have their own actuator, right? So those little flight controllers on there, you have an enable disable switch, right? So when you enable those, then that means the Q drone 2 is ready to go. It's armed, right? So yeah. So you power it on, and then when you're ready, then you enable it, right? And then if you're not using Q drone, you always disable it and power it off to save on the batteries. Make sure the batteries never go too low, right? These types of batteries, I think, although there's some power saving measures, always make sure the battery level doesn't go down too low. So please review the hardware manual that discusses that. So if we kind of look at that just for 1 minute, and if you go to you should have your Quanser folder in there on your ground station. So if you go to user manuals and you go to QZone 2 and you go to user manual hardware, then it will show you all that information here. So it'll show you the battery information here. So if the voltage drops below 10.5, then a low battery warning will show up, right? And if it goes below 10, then it'll automatically shut down. But always make sure, and then it shows you the charger that you guys have and all that. So make sure it doesn't go down too low. Any questions about that?
How can we check the charge?
The LCD screen tells you.
Where is the LCD?
LCD on the Q drone.
I have a question regarding the Jetson Nano. How much does the processing take
Here.
of the GPU in percentage?
LCD screen here on the Q drone 2. This will show you the battery level. Shows you the IP address and the battery level.
Excuse me?
Yeah.
I have a question regarding the Jetson Nano, the GPU. How much does the processing take of the GPU? Is it 90%? Do you sometimes face a 100% load?
Not sure I understand your question.
So the average processing for the drone, the
The
graphical
average processing?
the processing consumption, GPU percentage usage.
We don't use a GPU.
But isn't it the Jetson Nano an ARM APU?
It has a GPU, but we don't use it for the controllers.
Uh-huh.
Business spec.
The core controllers just target the processor. We don't use a GPU.
So it is just transcoding the cameras to the computer, right?
Yeah. I mean, I look into it in more detail if it's leveraging the GPU at all, but yeah, I can look into that more. I don't know offhand, but I'll look into it. Are there any other questions?
No questions, no.
Okay, so the Quark Rapid Controls prototyping software. So in here we are we're only basically using Symlink and Quark. So there's no Python examples for the Q drone, just to let you know. But at a glance, just as a refresher here, this is basically Quark in a nutshell, right? So you have these Quark hardware blocks, right? And you're going to be seeing these when we do the hardware test. So these blocks allow you to talk to hardware. So that's something that Quark brings to Simlink, the Quark targets library that allows you to use the hill initialize, hill read, hill write block. That is used right there from like a 2-channel DAC right up to a QDrone 2. You do have a lot of help pages, so I encourage you, if you want to know more information about Quark, not after this call or whatever, you can look at all the examples, right? And you can access those by typing QC_show_demos, or just through the help page, you can see the Quark software in there, Quark supplementary software. So there's a number of examples, Quark demos that are very helpful. But basically that's the hardware interfacing here where you have the hill initialized. This is where you set up your DAC or your device. So in this case, this would be the Q drone. And then the hill right are made to apply to the rotors, to the speed controllers, and the hill read here would be, you can use it to measure analog sensors, or you have one hill read block, which we do for the QDrone 2, which allows you to read multiple sensors like the IMU and stuff like that. Note that the QDrone 2 has 2 IMUs on there, right? So you have a 3-axis gyroscope, 3-axis accelerometer, but it has 2 IMUs. So in here, this shows you basically how the QDrone 2, right? The QDrone 2 hill initialize be configured to your QDrone 2. Then you have a hill write 2, which applies a PWM signal, and as well as digital signals to enable it and stuff like that. So it's a very, very low level, and you're accessing the IMU data, optical flow, all that stuff, right? So you have a very low level command of the QDrone. So that it's a very open architecture system. So as you know by now, the Quark, it supports different targets, right? Because if you have a QBot 3 or if you have a QCar, they can all support different targets. The other thing to keep in mindful of that you guys are kind of used to now is in the code generation, right? So code generation is where you generate your real-time code. So you click on Monitor and Tune under the Quark tab or under the Hardware tab, that generates the real-time code and downloads it to your target. So the way this works here now is you have your controller design and all your model design in Simlink is done all on the host ground station PC, and then you download the Quark controller on your QDrone 2, right? So you might have just one controller running on the QDrone 2, like the hardware test, for example. You just need to run it on the hardware on the QDrone 2 and just monitor the signals and apply signals to make sure everything's working. But often what you'll have is one controller running on the host, one controller running on the QDrone 2, and they're talking to each other. I was like, having a mission server that again sends the OptiTrack camera information, sends commands, and then the QDrone 2 uses that to get a better pose measurement, and it responds to the commands and stuff like that, and then you'll get the measurement back from the QDrone. So all the sensor measurement from the QDrone 2 is being sent back to the Xavier and can be sent back to the PC. Any questions about that's exactly basically like the QCar. Only in the QCar, we were never using a controller on the host that communicates to the controller on the QCar. You could have that, of course, it wasn't needed in the applications we did. For the QDrone, that is. Okay. Okay. So this is basically a setup very similar to that you guys have, right? Except you have a QBot 3 and you have a QDrone 2. So your ground station PC, I believe, is already connected to your router. So you should be all set. And what we were running is basically the basic communications demo, where you have the server running on a ground station PC, and it's sending a sine wave. And then you have the Quark basic client demo running on the QDrone 2, or it could be a QBot, it could be whatever, it could be the QCar. So this is running on the QDrone 2, and this is sending a sawtooth wave or a square wave, right? So basically the client, you should be receiving the sine wave from the server, and the server should also be receiving information from the client, this sawtooth wave from the client. So to make sure that, yeah, each one is talking. So this is a good test to see if the core communication works. So after you do the ping test, you can go to that, right? So you run the ping test and then you run that communications. Now you have to make sure that when you're configuring the client for the core communications is you need to set up the target, right? So for that case, because the basic communications demo is kind of universal, right? It's meant to be run on a local machine or on it could be run on any kind of target, both local and remote. So when you configure this for the client target type, you would by default it's set up for Windows PC, right? So you need to change that so it goes on, so it's targeting the Quark Linux Qdrone 2, right? For that NVIDIA. Once you do that, then you enter the IP address. So in your MEX file argument, you would enter the IP address of your Qdrone 2. This is very similar to what you did with the QCar. So this will show you a bit more information because now you guys are a bit more experienced because you use the QCar. This will give you a bit more information of how to configure the Quark models for different targets. The last thing you need to do is you need to set up the URI on the client, right? So when you're running something on the controller, when you're running a controller on the Qdrone 2, it doesn't know where the ground station PC is, right? So you have to tell it what the IP address of the ground station PC, so it can send its signal back to the ground station PC. So those are the three things you configure for the model, called the client in this case, running on the Qdrone 2. Any questions about what you guys will do in this example? Does that make sense, guys?
Yes.
Yeah.
So basically, you should see this, right? Your server is running on a ground station PC. So in your receiving data scope, you should be receiving the sawtooth wave that's being sent from the drone. And then on the drone, you should be receiving a sine wave that's being sent from the PC. This is what you should see when you run this demo. That is basically your starting point to understanding this client server configuration that we'll be using very much in the next in this session and tomorrow. So maybe we should so then we'll do the hardware interfacing. You want me to I can keep doing that and then we can switch gears and you guys can go through the hardware interfacing and the communications example.
Yeah, fine.
Yeah, so after we do the communication setup, that'll be kind of your first exercise. Then the second exercise will be running the hardware test. So we're going to run two hardware tests. We'll run one called the IO check full. So IO check full, basically, this allows you to test the motor commands to make sure all the speed controllers are working and that the rotors are going the right way, right? So you arm the Qdrone and you cycle the speed controllers to make sure the props are going clockwise and counterclockwise according to this configuration here. So if you have the front is basically where the camera is, and you have the back where it's where you don't have the IntelliRealSense camera, and then you want to make sure that the rotors when they're rotating, two of them are counterclockwise, and two of them are clockwise, right? So you'll see when you open the Civic model, it'd be more obvious. You can see this little diagram. The other thing you can do is you can monitor the battery status. You can also look at the height using, we have a height sensor on the Qdrone 2. You can look at the optical flow data, so the X and Y position, pixels per second. You can look at the attitude measurement as well, like the estimate. So using IMU, it has a Kalman filter that estimates what the position, the XYZ position is of the drone. And then you also have a camera check. So you can read the full, all the cameras, right? So the CSI cameras are using the video capture blocks. And then the video 3D initialize is set up for the Intel RealSense RGBD. And in there, you can get the depth measurement and the RGB measurement from the Intel. So this is just like in the Q car, where you are using the video 3D capture, but they're configured for different streams. So the stream could be RGB, could be depth, could also be IR. And the last one here, the video capture here is for OmniVision. I think that about covers it. Let me just see. So I think you guys will be. Hold on 1 minute. Just want to make sure. Yeah, I think. Yeah, yeah, we're all set. Okay. Okay, so I'm gonna stop sharing my screen, and then you guys can share your screen, and we can go through the first example. So we can run either the hardware test or we can run the basic IO test. So
Okay, first I think we should place the folders on correct location. Right now we do not have any.
wait a minute. It should already be placed for you under Documents Quanser.
So we do not have Quanser folder in the documents, but
Okay, that means the setup file was not ran on this user. I
No,
thought we
I
had done
think-
that actually.
I think the files are present on the desktop. Let me show you. Qdrone, yeah. Search resources and then source, yeah.
Oh, hold on,
Okay.
hold on. No, wait, go back.
Okay,
So this, you need to run the setup file to configure this.
okay.
But I don't know if this is the most recent one, right? Yeah, so let's make sure you have the most recent resources. I thought this had been done before.
Yeah, I think these are the recent one, probably.
13 September.
Yeah.
When was this? Is September
13.
13th? Yeah, that's fairly
Yeah.
new.
Yeah.
There's one other new build actually, so it's best to get the newest one. So let me show you the link
Okay.
on chat, or do you have the link already?
I think we do not have.
Okay, I'll share it in the chat. Okay,
Yeah.
okay, try that out.
Yeah. Started. It's gonna take 10 minutes approximately.
Okay, that's no problem. So while that's downloading, we can do the basic communications example, because basic communications example is based on a core demo. It is not, the files are not in research resources, because that's for anything you're doing. You can use basic client this demo you can use for all kinds of different applications, not just Qdrone. So
Okay.
open up MATLAB.
I think we have to.
Something like that.
What's that?
Yeah. It's opening. I think we have to power on their drone, right?
No. Oh yeah, you will be. Yeah. But you don't need to enable.
AICs.
That's right. You don't need to enable that because we're not running any. We're not driving any of the rotors.
Yeah, just up to
Battery.
Yes.
How to expand the battery.
switch. Where's the switch?
Is in all of them switch.
It's disabled. Just find the IP address as well.
Disabled, right? Red light is coming.
Yeah, it's disabled. Yeah, you just tell her the IP address. So
Thank you. Why is
here is
not
here is the LCD. It's gonna take a few seconds here. So you will see the voltage and the IP address.
Okay, then how can we recharge it?
You have to
Disconnect.
pull the battery out.
Charge the battery separately.
You have this.
Okay.
Next one to spare batteries.
So we have 16.5 volt now.
It is a nominal voltage?
No, it's fully charged now.
Okay.
So its life per cell maximum is
Okay,
4.2.
then where is the IP address of this?
The display.
Yeah. 192.168.2.10.
Okay.
Okay, now you can place it. We are ready for the print test.
Camera should be outside, right?
Yeah, fine. What's IP address? 2.10, right?
Yeah.
It's communicating.
Okay, great.
Okay.
Okay, this is
Okay.
command module, right?
That's perfect. Now, let's see what IP address the ground station PC is. The default is 5, but it might be different. Okay, so yours is 3.
3, yeah.
Oh.
Okay, that's good to know. Okay.
Simulate.
Visible, right?
Yeah. Says it, fine.
Okay, so to access the demos, the different ways to do it, but here's one. You can type Q as in Quanser, C,
You see.
underscore, show,
So
and underscore, demos. Yeah, demos with an S.
Okay.
Yeah.
Okay.
So here's a whole bunch of, so this is what I was kind of showing you before. We have a whole bunch of different core demos, but we'll just jump right down to the communications one. Yeah, so the core basic communications, note there are some different ones if you want to do more advanced, but for our purposes, core basic communications demo will be perfect. And you can go ahead and click on open these models on the top right. It takes a little time.
Yeah.
So again, so we're running the server model will be running on your ground station, but the client's running on your QDrone 2. So that's the one we need to configure it to run on a remote target and on a different type of target because we're not running a Windows, we're running a NVIDIA Xavier Linux OS. And then we're going to tell it where the IP address of the ground station is so that it knows where to send its sawtooth wave back to. And then we should see the sine wave and the sawtooth wave on each of the receive scopes. So that's the plan.
Okay, we have the models open.
What are we going to control now?
No, it's communication.
It's
Okay.
communication then. Okay, so
The computer will send the sine wave to the drone will respond with a sawtooth signal.
this is the client, so
That means they are communicating.
Correct. Go to model settings. Yeah. So if you go to code generation,
then we have to
click on the main folder first. Code generation. We need to change the target type.
okay.
You need to do that first, right? So you go to browse.
Fine.
Because right now, so as you can see, the system target file is set up for Quark Windows 64. So what that means is what?
Computer, PC.
That's right. Windows PC, right? But we're using this on a drone, so we need to therefore change the target.
Yeah. So Linux Q drone true.
Yeah. Click on OK.
Fine.
Okay, so next we have to say, okay, go to the interface panel, and then we need to add that line where we want to download it to the Q drone. So the line for that is going to be a comma, and then you put the indent.
Space.
Indent.
Space or
The not the exclamation mark, the single quotation mark.
Okay. Fine.
Then TCP/IP.
TCP/IP.
Yeah, colon.
Colon.
Slash.
Slash.
Then the IP address.
9.168.2.10.
Yeah. Then colon.
Colon.
Then that's the port number. So the port number is automatically configured for 17,001.
Okay.
And then you close the
Okay.
single quotation mark. That should do it.
Does it have? Do we have this documentation?
There's documented. Yes, everything is documented, guys.
Okay.
In the Qdrone 2 documentation that you're downloading right now.
Okay.
It shows exactly step by step how to run this demo.
Yeah.
Okay. Now it's
okay.
done.
And the last thing here is your stream client, right? So yeah, you can't save it because it's a demo. You can't save it because it's a demo.
Okay. Okay. So
You would need to save it under my documents or something like that. You need to go file save as and save it in another location. Because right now it's in yeah. Okay, you can click now on the stream client.
Sorry.
Stream
Click
client.
on the stream client.
Stream client.
The block.
Stream client, the block.
Oh, okay.
Right. So right now the TCP is set for local host, but we don't want to send this sine wave back to itself. We want to send it where?
The PC.
PC, ground control.
Correct.
PC.
Right. So you need to enter a local host. You want to change that to the IP address of your computer.
Okay.
Thank you.
191.2.3. Okay, fine.
Same port. Same port. 17,000.
Okay, we
That's it. Click on
change
OK.
that.
Okay, so that should be good.
On the server first, don't. Click on that client. I think.
All right. Yeah, let's okay, so let's go ahead and run the server first on your PC.
Okay. We have to go.
Yeah, go to Quark.
monitor into.
Correct.
Okay.
And this will be very similar to what you guys will be doing later on when we're doing like the hover test, for example. You run like a mission server on the ground station PC first, then you run your flight controller on the drone. So right now we're kind of mimicking that, but just with this basic client server demo. Now try running the client on the QDrone 2.
Okay.
Okay, so we're not. Doesn't look like they're communicating.
Server block has a local host in it.
Hmm?
The server block.
Hmm.
It says local host in there. See this? It says local host 18,000. In that block.
Shouldn't we change the model setting and the server
Yeah,
model?
we didn't change anything on the block.
Yeah.
Okay, hold on. You sure you entered the right? So it's running on the QDrone 2, that's for sure. Oh, the stream server. Yeah, maybe we should send that to configure the stream server to be sent to the drone. Yeah, the stream server, the IP address there. Yeah, set that to the drone. Mm. Jeez, it's very bizarre. Yeah, your stream server should just be sent to localhost. So that was correct before. Uh, you double check. Okay, go to. Yeah, no, if it would have given you an error if it didn't download. So what's the battery level on the Qdrone 2? Oh, there you go. Yeah. Okay, perfect. Okay, so now your server is getting the received data, and the server is getting data from your client, and your client is getting data from the received data client is getting the sine wave from the ground station PC. Does that make sense? Hello?
Sorry. Oh my God. Yeah, it's clear. Since client scope. So client receive this sine wave from this PC. Client is the drone and server is this ground control PC. So this scope is on the PC. It receives server from the drone. This scope is with this one. This is with this.
Yeah, but now the signal is different, right?
Yeah,
Why?
because both are different, sending different signal.
Okay.
One is sending startup wave from the startup wave is coming from the drone to the ground control. And sine wave is going from the ground control.
Okay, because in communication, one sending and other receiving, right? And server is send, and the client will receive that signal.
Both are sending. Both are sending.
Now both sending.
What's that?
Yeah,
Yeah, it's clear.
Okay. Okay, good. Okay. If you guys understand what's going on here, if you have no questions, then we can move on to the finalizing the setup of your resources. I think maybe your file might be downloaded now.
Yeah, it's downloaded.
Excellent.
For the camera?
Of the for everything camera test. So we have now the zip file in the downloads folder.
Move it to the other screen so you can see it.
Okay.
Nice.
So you have to unzip. In the downloads.
Yeah. And then you want to run the setup file.
I'll leave it with you.
Okay. Set up file.
same, I used not access, I don't have access. The one who was shared to have access. Yeah, so that's not. Exactly. So the longer than I that access directly to the laptop. Yes.
Yeah, it'll download some of these Python things. That's okay. I mean, basically we want all the users to be using the setup file because that always gives you the most recent material, right? So if you ever do any updates, then you basically will know what to do. So this does all the work for you. Now, if you go and modify a whole bunch of files and stuff, then it's a good idea to maybe save that in another folder if you ever do another update.
Well, now we have the Quanser.
So now it's
folder.
installing the source material. Okay, good. You have that. So we'll let that, it's almost done. So let's just let that finalize. But in the meantime, so we'll be running 2 hardware tests. We're running the hardware IO, and then we'll run. So in here in the user manuals, you'll see some documentation about the QDrone 2 if you ever want all the hardware information about the cameras and stuff like that. So you can open up the folder user manuals. You'll see QDrone 2. So you have all the user manuals for all of the devices you have, right? The Q car, the QDrone 1, QDrone 2. And then you have your user manual, right? So the power is, I think, how to do the charging of the charging of the batteries and stuff like that. The connectivity guide, the system hardware outlines like the hardware, the cameras, and the processor, the expandable I/O, stuff like that. Okay, so if you back up and go to Quanser, the main folder, then you also have now, if you go to setup, you can just click on yes. We don't need the Quanser libraries for this, so.
Okay.
All right, so go inside Autonomous Vehicles, Research Studio. So this is basically the step-by-step on how you set up the system, right? And we'll be going through all, much of this today. So for you guys now, we'll be doing the IO check, and then we'll basically go back and we'll go, we'll test your joystick and we'll test the, we'll do the rigid body definition and test that as well. So we can, yeah, we should be able to go through all of that in due time. So you can open up your MATLAB and then go to step 12 IO check.
Okay. Okay. Yes.
Okay, great. So go to QDrone 2.
QDrone 2 IO check. Yeah.
And let's open up the first one. Actually, IO check. Let's start with the IO check and then we'll do cameras.
Okay. Scope is so first we have to configure the model as interface. Then
So we will need to arm these systems, right? We'll need to enable the speed controllers. So for that reason, just make sure that the drone is not near anybody and inside the net. So just, you know, safety first.
fine.
One drone or both drone?
No, just
Just one.
this drone which is connected. Okay, now ACs are enabled.
Excellent. Because I'd like to run the motor commands first. We can test the motors.
Okay, fine. Okay. Should I enable the?
No, that
Mhm.
the ESUP, you don't
No, no.
need to do anything there. Yeah. So you want to arm it.
Fine.
So
It's
that is armed now, and then you can cycle the motors.
Okay, now it's motors are now running.
The motors are running?
Yeah. Rotate.
Okay, yeah, they are. They're probably running all together, right?
Yeah.
Yeah, I see it now. Yeah. Okay, so now what you can do is the second test is to cycle through the different motors. So if you
Okay.
do that, then it'll activate one at a
Okay.
time.
Yeah.
So here is the map. So if we provide
So
one,
you'll see two props. Yeah, exactly. You
Mhm.
follow that diagram. Which ones are counterclockwise? Which ones are clockwise?
back. If it is one
That motors. What does it mean? What does it mean of these ripples?
what
Ripples, these ripples, what do they mean?
is called is
Yes,
graph.
ripples, yes. And
It's written.
Yeah, so it's commanding each one separately, right?
Yes.
Okay,
Yeah,
so it looks like everything's okay, but you guys can confirm if it follows that diagram.
Front left should be count clockwise.
Yeah, correct.
Clockwise, then counterclockwise, then clockwise, then counter. Yeah, they are fine.
Okay, so you can put the switch back. You can disarm it now.
Okay.
And now we can test the sensors. So you can leave this controller running, just now deactivate the speed controllers.
We have to disable
And we can look at the height using the TensorFlow.
Okay. You have to be there. Okay. We have to sense where is the okay. The height. Yeah.
Yes.
So no, just you have to say it to height.
Okay.
Fine. Okay, a lot of noise. Yeah.
Still
You
high.
guys are zoomed up to a small granular on the scope, like,
Oh, yeah.
so, I mean,
That's correct. Sorry.
so change the scale.
Yeah.
You can put it on the ground and then lift it again. It will
Yeah,
be
lift
just
it up, but then, yeah,
Yeah,
There.
fine.
Yeah. So you
That's
can
okay.
see it's measuring about that, and then you can monitor the optical flow. There's the next one.
Okay.
So this will give you basically a sense of the X and Y. So if you move the drone and the X and Y, the planar positions,
Left.
X
right,
and Y, not height.
Yeah. How much? I think it's zoomed out too much. We have to.
Purpose good.
Yeah, no, it's okay.
Yeah, so it'll give you basically a response of where you're moving. If you're moving in the X or the Y, it should give you a response
Yeah.
in different directions, right? So
Mm.
plus X or negative X, plus Y, negative Y.
Yeah. The height is done. X, Y. Altitude estimate.
Yeah, so the attitude will give you it should give you the XYZ as well as the roll pitch yaw. So it'll give you the orientation based on the IMU. So that's as I said, it has two IMUs and they each have a gyroscope and accelerometer.
Mhm. Yeah, it's working.
So this is an estimator on there, and right, and the estimator is used in all the flight controllers, right? So it's basically using both IMUs to estimate its pose, but then it's also using the OptiTrack camera, the direct measurement. So it's using all three things to get the most accurate. Now, in this example, we're not, of course, using any localization yet, but
Mhm.
it's still doing some estimation on its own.
Fine.
So this confirms that the IMU sensors are working.
Yeah. The battery. Okay. Yeah.
And then you have your battery level.
Yeah. The battery. You can check the voltage here as well. Increase the battery. Okay.
Okay, great. Okay, I think you can click on stop. So if you click on the QDrone 2 DAC block, then this basically shows you the different sensors, right? Now, for example, if you look at the ranging sensor for height sensing,
Height
actually,
sensing. Yeah.
let me, yeah, so the range, yeah. So in there, that is, if you double click on ranging sensor, that is using the time of flight sensor. That's what I meant. So the time of flight gives you a distance in meters, and that is being filtered and gives you a height, right? So that is one being used, but it's being integrated with the height measurement from your IMU sensor as well. If you go, so you have your optical flow measurement as well. So optical flow is being measured. Yeah, if you go to Hill, yeah, it's not there. It's yeah, the optical flow is measured from your Hill read. So if you go to your left, yeah, and just zoom up on the Hill read. I just want to show you a bit of this. So Hill read is like kind of like the one that reads the most information, right? The Hill read is directly interfacing to the DAC, right? So the camera blocks, and the time of flight blocks are kind of, they're separate blocks unique for that device, but the DAC, anything that's connected to the DAC will go through the Hill read. So this Quark block interfaces to the IMU. So like I said, you have two IMUs, so it's getting all the sensor data from there. Your optical flow, the RPM of your your speed controllers, stuff like that, the voltage of the batteries, motor current, all kinds of stuff. And then you, on your hill right, you're commanding the PWM and any LEDs, the digital LEDs you're commanding. So you're getting a very, very low level command there. So this is, although this is a simple IO check and test, it's a good way of showing you a deep dive of the level of access you have to all the sensors and actuators, right? So it's very, very low level. This is what allows people to do research, right? Because you have low level access. That means you can design whatever control you want. Any questions about this?
How can we change the controller? Which controller is the quadrotor using here?
There's no controller on there. We're just doing a
Okay.
hardware test. I'm telling you, when we get to the controller parts, they're all based on the same thing. They're all based on the same hill read, hill write block. So you can modify all those controllers and models for your own purpose, right? But this is not running a controller. It's not running any flight controller. We're going to get to that. But you could ultimately modify that for whatever control you want. And people have done that, right? That's one of the reasons people like using these systems. Any other questions?
In regard to height sensing, does it use a combination of optical and gyroscope sensing?
It uses, for the height, for the flight control, it uses predominantly the OptiTrack height measurement, but it's also using the estimate from the IMU. I don't know if it's, I don't think it's using the time of flight, but it could as well, right? Because for the most part, what you're getting XYZ position using the two IMU sensors, the estimate of that, plus the OptiTrack camera when we get to the hover test. So it's using those three sources of data in a complementary filter, Kalman filter observer to estimate the height, the X and the Y of the drone. Again, this is only a hardware test to test the different sensors, so it's not doing that observer design here. It's doing a bit of it, but not the whole thing. But you can see in the IMU attitude estimate, it does do some estimation there using the complementary filter.
Okay.
So in this particular example, if you look at, it's showing you the height that's estimated from the IMU and the height from, well, the ranging sensor, the time of flight gives you a direct height measurement, but if you go down to IMU 0 attitude estimate in the bottom left, this shows you basically the basic sensor fusion we're doing there. So as you said, your height is actually getting it from the gyroscope.
Okay. Fine.
Any other questions? Okay. Let's run the camera example really quickly then.
Okay. Okay.
Okay, excellent. Perfect, yeah, good. Yeah, go ahead and run that. And then you can look at the different information. So note that the depth for RGBD is going to be colorized, just like in the Q drone. Do you have the covers on the CSI
Yeah,
cameras?
Probably, yeah. Please remove the covers. This side and back camera. Okay. Okay. Yes. Pick the drone up and rotate it. Its face is towards us.
So yeah, you're pretty much seeing all the cameras there. If you lift up,
Yeah, lift it up. Yeah, line that. I think we have covered over there as well.
the downward
Down facing,
omnivision
yeah.
camera.
Down facing camera. Yeah, there. Okay, fine.
Oh, that's why you weren't getting.
Yeah.
I was wondering because the optical flow usually gives you.
Yeah.
I was wondering
Oh.
about that. It's like this didn't seem right
Yeah.
to me. I forgot exactly what the response was, but it didn't. This
Check
time I
it.
made it didn't feel it didn't look right. So if you reran it, you'll get a better measurement. Good thing we weren't using that in a controller. Yeah, we would have found out pretty quick that the cover's on. So yeah, guys, this is a lot like the Q car, right? So you're getting the left, right, and back cameras are the CSI cameras, and then you're getting the OmniVision, which is the downward-facing one that's used primarily for optical flow, as we've seen it with the Hill Read block, and then the front camera is your RGB and Intel RealSense RGB and depth camera. The depth measurement is just like in the cards pass through that colorized block to kind of give you an indicator of which objects are far, which objects are close.
Okay. Rotate it. Yeah. More. Fine. Okay. Fine. Good. Thank you. Okay.
All right, excellent. Any questions about that?
Do the 4 cameras actually cover the 360 degrees of coverage?
Almost. It depends on their field of view, right? So, the field of view of, I'm not too sure what the field of view of the, if we look at the user manual here.
Yeah. I think it's covering. From the cameras, we can see the images are overlapped.
Yeah, the CSI cameras in the back will give you 270, but the front camera,
Example like here.
so I'm looking at the data right here. So in your user manual hardware, it gives you the field of vision of the different cameras, right? So now the horizontal field of view will change depending on the resolution, but for the CSI cameras, it's the same. It's 160 degrees for the CSI cameras. So each one, the field of view for horizontal is 160 for the CSI cameras. But for the RGB, it's actually about 42. 42, right? So you're not getting the full front, you're not getting full 360, but pretty close.
Okay.
Because the CSI will give you basically like 80 degrees plus 80 degrees. But the RGBD camera is like this. It's like 40. It's like 42.5. Why were you asking, by the way?
It's so that the images overlap and it is necessary to get a coverage of the surrounding to detect any objects that might actually block like another drone or you know,
Yeah.
some feather, for example.
I mean, you're getting most of it, right? You're not getting a full 360 like the Q car you are. In this case, you're not getting a full 360, but I think it's probably enough for doing for detecting most objects, right? Because you're getting like, because each one is plus 80 minus 80 for the CSI cameras on the right and left, and the back one, and the front one is plus or minus it's 42 total, so plus or minus 22.5 or whatever. So the front camera, you might have a little like, you might have a little blind spot there, but not very much. Any other questions?
No.
Okay. Okay, you can stop this model. And you can go ahead and actually turn off your drone.
Okay.
Just
Turned
save
off
on the
the-
power. Okay, great. So the next thing we're gonna do is define the rigid body objects.
Yes.
So let me basically show you a bit of this information.
Okay.
Uh, so in here for OptiTrack localization, like I said, basically your camera here, you're measuring the pose of different rigid objects, right? This could be any kind of rigid body. It could be drones, Cubot 3, could be, you know, whatever object you define using those markers, right? So all the different systems have different markers. And those are basically shown if you look at, I show you here. And defining the rigid bodies and motive. So this is the user manual in here. You'll see that the different markers are kind of like this, right? So you'll have, for example, in the QDrone 2, you'll have different markers placed, right? So the markers are configured so that it's unique for each object. So as you can see here, QDrone 1, QDrone 2, Qbot 2 or Qbot 3, any kind of different vehicle, you need those markers, right? But the markers need to be positioned, every single one needs to be unique so that it can identify a unique rigid body, right? Because if you have multiple QDrone 2s, then those are arranged differently so that you have QDrone 2 as different rigid bodies. So if you want to do swarm examples, you can do that. The other thing to keep in mind, these are all like pre-done before they're shipped, but if you ever have to do it yourself, then also note that you don't want the markers to be symmetric. So you don't want like a square or a circle. They should be asymmetric, right? Because that way, if it's symmetric, then it won't be able to tell like the roll or the pitch or whatever like that, right? Like it won't be able to get all the right positions. So it has to be asymmetric.
Think the markers, we have two drones and both have markers on
Yeah.
identical position.
Identical?
Yeah, I think so. Can you please?
Unlikely, very unlikely.
Yeah, रहीम इन दोनों को उधर खड़ा कर दे कैमरे के सामने. हाँ नहीं कर वो देख लेगा ना क्योंकि कंफर्म हो जाएगा दोनों को प्लीज.
Yeah, identical.
Side by side like that. Yeah, just place it there.
Okay, both are labeled Q-Drone 2. Both of them are labeled
Yeah.
Q-Drone 2.
Sorry?
Both of them are labeled Q-Drone 2.
No, not the label. You can see that the reflective small bob on the stair, small spheres. So those are the markers,
Okay.
not the writing. Both have markers on identical.
They are?
Yeah, there. We actually showed you in the video as well.
Where is the marker?
It's the same marker.
Oh, yeah.
Both are identical.
In that case, then you can go to your rigid bodies. There's here are the different configurations you can use. There's many different examples. Again, guys, I'm reading the PDF that you just downloaded, right? So make sure you open up the rigid body motive so you know where everything is.
Okay.
So I am under step 11, rigid bodies. If you open up this PDF.
Yeah. Okay, we are there.
Right, so this shows you different marker configurations for each device. So ultimately you can always remove those and redo them. If they're identical, then they should not be. Because later on you might want to do like a swarm example or something like that.
Yeah, correct.
So once you define all those unique markers for each of the rigid bodies, now basically the way it's positioned, you have the ground station PC, and the way you do it is basically you'd go through the calibration. So the calibration is called the wanding procedure, right? The wanding procedure, basically you have the wanding and you go around and it collects a whole bunch of data. Now what that does is basically it tells the camera where they are with respect to each other. So that's one of the things that calibration procedure will do, right? The cameras know where they are with respect to each other, right? And then when you're defining the axes, you have what's called the grounding plane, right? This little widget here. So you put that in the middle of your workspace. Now this is important because this is what defines the axes of your workspace, right? So you want this grounding plane, you want the Z of the grounding plane to be pointing towards the ground station, right? So that you need to make sure you do that because all the files are defined with respect to that configuration. Right. So when you put the grounding plane, it basically does two things, right? It tells the OptiTrack cameras where the ground is, but it also defines the axes. So those are the two main things it does. So again, you always want to make sure that you set up the motive grounding plane so that the Z is pointing towards the ground station, and that will define the motive frame of reference. Now the research studio frame of reference is different. So we do basically a rotation of 90 degrees, and that will basically it's called the research studio frame. We're doing that because that's the frame that is used. It's more a standard frame of reference that's used, right? But just so you understand, that will be clear once we use that OptiTrack visualization demo. Now, when you define rigid bodies, you have to make sure you define them properly. So you need to make sure that the front of the vehicles are pointing away, right? Away from the ground station PC. Because that will define, because that way you basically, if you do your axes like this, right? You have your X, Y, Z. Your X is the front. So your the front of the Q-Drone 2 is your Intel RealSense camera, right? So that's your front. It should be facing away from the ground station PC. That is basically the X, and then the Y is towards the left, and the Z is going up. Same for the Qbot. For the Qbot 3, if you define that, you want the camera to be facing away from the ground station PC because the front should be always facing away. And that will make sure the X and Y of the body, of the rigid body, is in line with the Research Studio frame. After that, you're all set. That's a very common mistake that people do, right? So that's why I'm really stressing that point, because often when something goes unstable, it's usually, that's one of the main reasons.
Yeah, so
So are there any questions about that, the frame of reference and how you define, like what calibration does, what the grounding plane does, the orientation of defining the vehicles? I covered a lot of information here.
yeah, I think it's clear. It's clear.
Okay,
Excuse me,
we'll reinforce it a bit.
How about the dimension of the, for example, the playground? So how can we define the area that should the drone be and not exceed to reach the boundaries, for example?
Yes, that's a good question. That is basically when the one way you can do it is basically you need to do it. You'll get a bit of an idea from, I think it shows you in here. So after you define all this and you go through your rigid body definition, so we're going to get through all this point. You go through your visualization. So I'm just going to show you if you calibrate your cameras. Okay, it's not showing here, but you get a capture volume here. The capture volume after calibration will give you an idea of the workspace you're dealing with. But ultimately, the best way is, and we'll be doing this very soon, is we'll be running the OptiTrack visualization demo. This is telling you when you're tracking the Q drone or any rigid body. So the tracking will be 1 when you're able to pick up that object. It'll go to 0 when you're unable to track it. That is a good way to basically mark out your workable space, your effective workspace, right? So that basically what people do usually is you just get a roll of tape and you have someone sitting at the ground station PC and someone inside the workspace. You move around the drone to different points around the workspace, and then you just make a note of when the tracking stops. When the tracking stops, that's your limit. So you put a tape down and you'll basically get like a circle. That's like the gold standard of defining your workspace.
So this point we only define the axis, right?
No, your workspace, the workable workspace of where the drone is being tracked.
Sorry. Now this triangle that we placed on the playground.
Okay, that's going back to what I explained originally. The grounding plane defines the axes. It doesn't.
Only.
It tells the camera where the ground is and it defines the axes of it. So that's why you need to be very specific in making sure the grounding plane, the Z, points towards the ground station PC, because that will define the motive frame and that orientation.
Okay, thank you.
You're once we do that, once we do all that kind of stuff, then you're kind of done with the motive software. So we'll go through step by step how to define the rigid bodies. So we'll first do the camera calibration. So again, as shown here, we define the motive frame as follows, and we'll go through the calibration, and you'll see all this stuff here. So I encourage you to be, so you can open up actually the calibration cameras reference frame, and you should be able to find your calibration 1 and the grounding square.
Okay.
And then we'll go through the different steps of doing the wanding. And here's an example of the point cloud you'll get when you're doing the wanding. And you want to make sure your quality is very high or exceptional.
Yeah.
And then once you get that calibration result, you click on apply. And then next step is to define your grounding plane. You make sure you set your vertical offset correctly to 19. And then you can look at your capture volume if you want. We might as well. Then we define our rigid bodies. So when we define our rigid bodies, like I said, you have your Qdrone 2 models, but you'll open up right after we do the calibration. When you place your object, you'll get something like this. You select all the markers, and then you basically create from the selected markers. And that will define your rigid body. That's basically all there is to it. Now, the other thing we can do to improve the stability, and I think we should, it's not quite necessary, but I think given you guys are more experienced, we should definitely do this, because adjusting the pivot point of the drone to make sure it'll be more stable in the flight. So we should definitely, we'll go through these steps too. It's a little bit tedious, but not too bad. But we'll just follow along the guide so that you guys know how to do it on your own after the training. Okay, so we'll do the calibration, we'll define the axes, we'll define the rigid body, we'll adjust that pivot point, and then after that, we'll run the OptiTrack visualization demo to make sure that it's tracking properly.
All right. So now we go with the calibration, right?
Correct. So I will, if there's no questions, and then we'll run this, and then let's go through this exercise first and see where that takes us. So you can go ahead and share your screen, and I will guide you through it.
Right. Okay. The software is already opened.
Okay, so you don't want the calibration, you don't want the grounding plane to be in that workspace, right? Because the first step is calibration.
Yeah. Okay. There is Miss.
So make sure you remove the grounding plane.
Yeah. Very much. I think I have to go inside by my own. Can you please?
Okay.
Red screen.
Stop.
Going around. Yes. Well, okay. Wait a minute. I will do it. Yeah. Safe work or not. Right. Yes. Okay, इनसे पहले पूछ लो बस वेट कर लो उनको. Okay, so it's removed, Mitch.
Okay, you can zoom out a bit using your mouse wheel.
Okay.
And it's a good idea to make sure that there's nothing else like reflective in your environment, right? So no, just exactly. So it looks like you're okay. Actually, see, the camera 1 is picking up something. If you look at your camera preview on your bottom window,
Yeah. Yeah.
what is that? It's
Okay.
picking up two markers.
Wait. I think, yeah, probably you have to.
Is that the wand?
Let us.
No, I didn't believe it.
What was it?
Small white sheets.
Okay.
Now it's removed, right?
Yeah, probably. No, actually, they're not. You just keep it outside.
No.
No, actually, the markers were inside. No problem.
It's a big pieces are there.
No problem from there. Okay.
It looks pretty clear, I think now, right?
Yeah.
Okay, so in the perspective view of motive in the top window, you'll see that the cameras don't quite know where they are with respect to each other or the workspace. So what we're going to do is the wanding, right? So when you guys are ready, you can click on the start wanding, and then you get someone to go in with the wand and do that procedure.
Just.
What are you doing?
Separating.
So you want each of the cameras to be, you want approximately at least like 6,000 to 8,000 points for each camera.
Yeah.
So when you're doing this, you're getting a pretty good spread, but sometimes it's good to have your friend kind of point out, okay, this camera is a bit low on the count, kind of stuff like that. You can navigate that to make sure that, make sure you go between the different heights, right? Low,
Yeah.
high. You don't want to move it too fast either. You don't need to rotate it like that either. I guess you can, but
The one in the this is the space. The opposite. Almost there. Yeah, you are now in the area which needs more points. Yeah, that's the one.
We have to fill on the leg push.
so camera 5 is a bit low. Camera 5 and right, so that's kind of what I'm telling you guys, right? Like, yeah, 4 and 5 need a bit more counts and as well as 2, but it's looking pretty good. We are at 6,000 for each. Yeah, a little bit more for camera 5, and we should be in good shape. Okay, that is pretty good, I think, guys. You have at least 6,000.
Camera 5, yeah.
Yeah, between 6,000 and 8,000 is good.
Okay.
Okay. I think that should be good enough.
Would doing more make it more accurate?
Okay.
If you do it more, if it'll be more accurate.
Yes.
No, the accuracy, no. No, the resolution is just dependent on the camera. You won't get more accuracy. You want enough, but actually, if you get too many points, it could lead to noise. So you want to make sure you don't get too many. So this should be decent. Click on, so now, okay, so you're done with that, so you can click on calculate.
Next year, then only we can I think it's good.
Yeah. Camera. Okay.
Okay, great.
Apply.
So now the cameras know more kind of where they are. So now the next step is to define the axes, right? The grounding plane. So this will tell the camera where the ground is, and it'll also define the frame of reference.
Yeah.
So make sure again that
No, just one time.
One time if you do. So every time you can do.
That's fine.
If you move camera, then only.
The center is this. This is the center.
Center, yes. No, that the mat is center.
Which mat?
That center mat. You are standing
Okay, here.
That,
yeah, you want to make sure it's in the center. Yeah.
Fine.
that is center.
That is, fine.
Okay.
Okay, so the Z is facing towards you guys, right? Towards the ground station PC.
Yeah, here is no Z actually on this. Actually, one side is the short one and the other is the long
Showing
one.
in camera. Short it.
This
Yeah.
is the this is so we face this side to the ground control station.
Correct, yeah. Look at figure 6 in the calibrating camera reference frames PDF.
Figure 6.
So in figure 6, it'll show you. I just want to make sure you guys know what document to go when you go back and do this yourself. But this will become second nature, guys. The first time it always takes the longest, but you need to do the calibration. I mean, there's no set. Yeah, go to page 7. Not rigid bodies. Go to calibrating cameras.
Okay,
Step 10.
sorry, just give us a second, please. Step 10, okay, so we will
Camera
go
calibration.
step 10, yeah.
Page
Hmm?
page 6, I think.
Page 6.
What's that? What's that?
Yeah.
Figure what? Figure
Mm-hmm.
6.
All right, so this is basically showing you, right? So if ever you're in doubt of how to define it, this will show you.
Mhm.
The next thing you need to do is make sure that you set your vertical offset, because right now it's set to 6, which is not. Oh no, it's set to 19. Yeah, you're okay.
6 is okay, right?
Yeah.
18 and 6 both.
Okay, you can minimize that.
Okay.
Okay. Click on set ground plane.
Okay.
And then you can, so you can maybe put this in another folder if you want. You can keep it under object track, but maybe another session name.
Yeah, it's already, I think the name is changed because we have different time.
Yeah,
and
the file name has changed, but your folder says September 14th.
Oh, yeah. Correct. New folder. I think we place it in the documents somewhere. Okay.
Great.
So So, okay.
Okay, good. That's kind of the first part of this. So now you can remove the grounding plane.
Okay. Which I have a question, what is this, this small frame which is showing over here?
It's not showing.
The axes.
I don't know, but it doesn't look.
Yes, Z-axis upside down.
Yeah.
Seems like the no, the
Drones.
marker of the drone. Yeah, this graph. This
Maybe it's something it remembers from another file, but
okay.
we'll be defining another object. So
All right. Yeah.
Before we go any further, may I ask about the vertical offset? Why did you decide to change it to 19 exactly?
19 that's from the manufacturer. 19 is what you should be setting at. That's the default for that grounding plane. It's not us that came up with it. It's from Natural Point. That's how they define that. There's different grounding planes, and the one supplied to you has a vertical offset of 19 millimeters. That's the height of the grounding plane that you have.
I see.
That's the standard. That's the default. Okay. So go ahead and move your drone inside the workspace, and we can define that.
The drone can function without the cue balls.
Yeah, drone doesn't need cue ball. Yeah.
Yeah, we'll just start with a drone for now.
Body recognized.
Yeah. So actually now this is on the correct place.
So now when you put the drone, you want to put it, looks like it's in the middle already, and make
Yeah.
sure that the front, which is the RGB D Intel RealSense camera, it should be facing away from you.
Yeah, 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 it's like that.
Camera is not showing
Okay, let me.
Yeah. So you can zoom up on that. It looks like it's already defined, but we'll know when you select it. So you can zoom up on it a bit and select that. Okay. Okay, so that is your rigid body. So you can right click on there, and then you rigid body, create from selected markers.
Okay.
Oh, see, you already had a rigid body defined before.
Yeah, actually it was defined before.
For some reason it picked that up.
delete the create again.
Oh, okay. Yeah, that's. Okay. Try selecting it. Okay, right click on it and go to rigid body again, and let's try removing that because we don't want two rigid bodies.
Okay, so I removed it. It's still rigid body too.
Okay, select it again.
Yeah.
Okay, go back to.
There's another remove in the menu. Select when you select.
Okay, hang on.
Oh, okay, so we have a remove for here.
Yeah, remove. Yeah.
Now it's remote probably. We
Okay,
do not.
click somewhere else on your screen.
Mhm.
Okay, select it again.
Okay. Okay.
Okay, click on remove.
Remove again. Okay.
Okay, there we go.
Yeah.
Because it's remembering, I guess, from the old session for whatever reason.
Yeah.
It loaded that file automatically, I guess. That's why, because we did this before, right? We did a hover test.
Yeah.
Okay, so now it's fresh. So now we can define our rigid body.
Mhm.
So now you can select that.
Create from selected
There, that's
one.
better. Yeah. Okay. So now you can see our name is rigid body and our streaming ID is 1, which is what we want, right? We want our default object to be 1. Otherwise, because when we have multiple rigid bodies, each will have a different ID.
Yeah.
That tells Quark which vehicle is which, right? But because we're just running one drone, we just wanted that one ID to be 1.
Okay.
Yeah, you could call the rigid body Q drone 2 if you want. Q drone, whatever you want.
Q drone 2/1.
Perfect.
Yeah. Okay.
Now the next thing, and this is probably, I think it's easier if you guys maybe open up that rigid body PDF.
Okay.
Okay, so you can
Just come back to the
open
page.
up this step 11 rigid bodies. We're done with that file.
Okay.
It's still open, I think.
Because now we need to just adjust the pivot, right? Because the pivot of the center of gravity of the Q drone is just a little bit down. So we want to move that in OptiTrack to have a better, the rigid body to be more representative of the drone.
Cassette to 1. Okay, fine.
Yeah, exactly, right? So yeah, you can go to view and the builder pane.
Okay. View and file edit view.
You don't have the menu. Oh, it's on your right. On your far right, that's where the menus are.
All right. View.
Yeah.
And then builder pane.
Builder pane. Builder pane.
Okay. Selected in the place, scroll down to mark 5.
Click on edit.
Edit.
Okay, so there you go. So now you so yeah, so right now you're seeing all the different markers. So if you have only one marker on the handle, find the marker in the list, since that's one position in the actual center of the drone.
This one.
Yes.
No, this one.
Is that the one on the handle?
Sorry.
Select the marker that's on the handle. Or in the actual center of the drone.
How to select it? Over here in the center.
Do it in a perspective view. You should be able to select.
Perspective view. Okay.
Yeah, go in there and select the one that's in the center.
Yeah, it's selected now.
Are you sure that's the one in the center?
No, sorry, this
No,
one.
it's this one.
Yeah, this one. Yeah.
Try selecting the other one, actually. I think that's not the centers. I think it was the one below. No, in this, right in the middle.
Yeah.
Okay, yeah, that's. Yeah, so you get in the XYZ position there.
Yeah. Total of
Okay,
5 markers. I don't
so
know,
now
but
if you, so in the properties on your bottom right, if you expand the properties, again, look at figure 7.
okay.
Figure 7.
Figure
But
7, yeah.
yeah, so
Marker of 5. Yeah.
yeah, marker 5 is your top marker, right?
Mm.
Okay. So then you want to enter that data. Wait a minute, is that doesn't seem right. Could you make your properties window a bit bigger so we can see? Just change the height. Yeah, well, okay. Can you look at all the markers?
Sorry.
Markers.
Okay.
I think it's marker 1 might be. What's the one before that? Okay, so marker 1 is your first one. That seems more. Yeah, so marker 1 is probably your top one, right? If you select, could you look at your perspective view and just hover over the first one? And what's that? Click.
Okay.
Okay, click back on the other one. Yeah, I think in your case, when you go down to your marker settings,
In
in properties.
properties.
Yeah, I think marker 1 is that, because it should be about like -10, 28, -36. So it looks like that's the one in marker 1. So what you want to do is copy marker 1 is the one that's in the middle.
Mm.
So you want to copy that inside your inside the location of XYZ to translate the pivot point.
Okay.
Uh,
So
that's shown in your figure 8.
fine. Yeah.
So the
Correct.
top center marker is going to be, is that the actual center of the drone, right? So we just want to use that as a reference. So you want to move the pivot point to that.
Okay.
Copy paste.
Okay. Copy and paste it. Okay. So this is. Okay. Apply.
Yeah.
Yeah, it's done. Translated to
Yeah.
correctly.
That looks good, I think, guys. Okay, after the pivot point moved as change.
It's correct.
Then change X and Z to 0 and the Y to -70 millimeters.
For which marker?
So then you set X and Z to 0.
So for
I-
this.
Yeah.
Okay, okay.
Shown in figure 9, right?
Okay, figure 9. All right, so
After we adjust, we go back to the 21.
0.
Yeah, because we're using that marker as a reference point to move the pivot point to the top marker. Then we know where the top is, and then from that, then we can bring it down to the center of gravity.
Okay, now I think it's apply, right?
Yeah.
Okay.
Okay, there. Yeah, that looks good. So now you've lowered the pivot point to be at the center of gravity of the Q drone 2.
Okay. Fine.
Okay. Okay, you can zoom out a bit and select that body and yeah, select that guy. So select all the markers.
Mm.
And then you can click right. Rigid body.
Okay.
Oh, sorry. No, go to file. Sorry, go to your file menu and you want to export that. You selected all the, oh, no, wait. No, you just select all the markers. Yeah, go to file.
File.
Yeah, and go to export assets.
Okay.
And you're in the right folder. So yeah, that's perfect.
And
Okay. That's good. So yeah, you can minimize motive. Usually we recommend closing it, but let's keep it open for now and let's open up. So now we can test to see. So anyway, are there any questions about what we just did?
Just one question. If the configuration of the reflector is different, for example, for the second drone, can you apply the same as if from the manual as we did before, and it will work just right, or we need to change something?
No, you just add that rigid body and define that second rigid body.
But in this case, the rigid body was not actually correct or fully correct, right?
I don't know what you mean.
We corrected the center of gravity.
Yeah.
So we need to, we have the second drone with the second configuration, right?
The second Q drone?
The second drone, we need the reflector to be set in a different way than the first drone, right?
You need to redo it for the second drone.
So when we redo it, then we create a new rigid body. We need
Yes.
to edit the center of gravity.
Yes.
We do the same as the manual says.
Yes.
Okay.
Any other questions?
All good.
okay.
Okay, yeah. So this is our other checkpoint, right? So we're going to do the localization visualization demo. So yeah, you guys can open up, you can go inside rigid bodies, step 11. And yeah, you can go with the first one. Okay, so yeah, so what you do here is no, because you don't need to remember this is running on your host. It's running on your PC, right? Because your cameras are connected to your computer.
Yeah. So no need for that.
But what you do need to do is define the new files that you just created, right? So you have a new calibration file, you have a new rigid body. So go inside OptiTrack and double click on that. And click on calibration.
Browse.
Right.
Okay.
So you click on calibration and then you go to the new file you defined.
Okay.
We use OptiTrack software to just to define a file.
Yeah. This is, I think, yeah.
Yeah, and then you want to define your
Rigid body.
your asset, your rigid body.
Okay.
They call it rigid body or
Cube
assets.
control. Okay.
Yeah, and you see right now your trackable ID is set to 1, which was a streaming ID that corresponds to OptiTrack, right? So if you had multiple vehicles, each one will have a different ID. 1, 2, 3, 4. Yeah. Okay, click on OK. All right. Yeah, go back to your main model and
Yeah.
go to your hardware or your Quark and click on monitor and tune, and we'll give this a shot.
Okay. Now we have to go there.
So now your drone is off, right?
Yeah, it's off.
Okay, so now you can test these axes, right? So this is showing you several things. So if you have someone go in.
No. You have to move it. Yeah.
Okay,
right.
so now you can see that it's moving, right? So the red frame is the body frame of reference, right? So as you can see, the body frame of reference, your X is your, if you do your frame of reference like that, right? Your X is your Intel RealSense pointing away from you. And then your positive Y is towards your left, and then up is Z. So this is in line, and then the blue axis is the Research Studio frame of reference, right? The blue. Now, what is the gray? Can someone tell me? Or the black or the gray?
Gray, the huh?
That was the motive frame of reference, right?
The
So the
motive,
motive frame of reference is kind of the software level frame of reference. That's what was defined in the grounding plane. But what the software does is it rotates it 90 degrees to be in line with the conventional approach of how drones are defined.
Okay.
This looks good, gentlemen. So that's a quick test to make sure that your OptiTrack files, the rigid body is defined properly, and your axes look in line. But this looks good. So that means that you're able to track it. Now, if you restore this window, just make it a bit smaller. No.
Zoom in.
Yeah, you can zoom up on it. Yeah. Now go back to your model.
My model. Okay.
So you can see that there's is tracking is set to 1.
Yeah.
That means it's tracking, right? So this OptiTrack block does gives you the position and orientation data, right? The complete pose, right? But it also tells you whether or not it's tracking, which is important, right? If it stops tracking, then that would set a watchdog and make it land. Now, what you can do is now, if you want to have an idea of what workspace you're dealing with, you can move the drone in different areas in your workspace and to see how big of a workspace you effectively have, right? That's what I was going to before. So if you go ahead and move that drone, because right now it's not on, so this is the perfect controller to use to define that workspace. Why? No, keep it on. Keep it here.
Okay.
You want to look at tracking as 1. If the tracking gets lost.
No. Okay, it's working.
Right,
now.
so it's working now.
Corners. Yeah. Go to the corners first.
See, now it's off, right?
It's 0. No. Okay.
So you don't want to go too high. So you know now that if it's like, if it's beyond 1.5 meters or whatever, that's too much, which is that's standard, right? Because your cameras are only so high. So yeah, and if you move it to X and Y and Z, then you kind of have an idea of what workspace you have.
Okay, fine. Now come to this side. So back there. Come.
You can see it, so we can.
You can come. Okay, go there.
Yeah, and then it loses tracking there, right? So,
Yeah. So this is our effective area. All right.
so given you have 6 cameras, that's pretty good actually. You have a pretty decent workspace. So the ways the cameras are set up for 6 cameras, that's quite good. You can't get much better than that, I would think. I mean, it's hard to say because looking at this like remotely, I'm not there, but it looked like this is good for sure. If you're using more cameras or bigger workspace, I mean more vehicles or more workspace, then of course you need more cameras.
Yeah.
So make sure you move that back to the middle and the front's facing away, I think it is. So that's good.
Yeah. It's correct.
Yeah, so that is what this test does. Any questions about that?
Can we use 4 cameras instead of 6 in this case?
What's that?
Can we use 4 cameras instead of 6 in this case, in this scenario?
Why would you want to do that?
Reducing the cost.
We always recommend 6 cameras. 4 is not enough. It could be able to get it, but not reliably. 6 is the minimum that we recommend for one vehicle. 6 is the best. 4 would work. You need at least 3 cameras to view the drone at each time.
Yeah.
Right? If you only have a 4th one, that's pretty tight. I mean, you might be wanting to cut costs, but if you only have a 4th camera, you need 3. That means the drone will be losing control pretty often. You'll be losing tracking. So 6 is better. More robust.
So when do we need more than 6?
I just said if you have a bigger workspace or multiple vehicles, you need more.
And they're going
If you have 4 vehicles, then you need more cameras.
Actually, same concept, field of view.
Okay.
You got it. So you want to cover next the space with the cameras. That's the thing.
So how can we, so that means we cannot design for mission control without installing more cameras, right?
I didn't say that.
Okay.
I said that if you want to operate, the question was when you need more cameras. You need more cameras if you're using a lot more vehicles. We are going to be doing mission control tomorrow. We're going to be doing the hover test tomorrow.
Okay.
This is track live test. What happens? Turns to 0 though. It goes to the area where it can't be tracked.
Yeah, ask louder a bit.
If
we
you
do
want
live-
to, what's that?
If we do a live test, what happens when it loses track in midair?
But there's a safety watchdog, so it'll land automatically. If it loses the
Oh.
tracking, it'll do its best to land. Yeah.
Okay, thank you. Yeah.
Yeah, let me show you. So if you look at, so we have a chart. So with 6 cameras,
Trying to find.
so this is on our website, but if you have 6 cameras, so if you have 6 Flex 13 cameras, then you can go up to like 3 vehicles. If you had 6 vehicles, then you need 8 cameras. So this is kind of our configuration, our recommendations, right? If you have more than 3 vehicles, then you need a larger workspace. You would need more cameras. It also depends on your camera type and stuff like that, right? But for your purposes, you can run 2 or 3 vehicles in your current workspace.
Airspace.
Okay.
24 camera, and their workspace is 14 meter into 9.
Okay.
Ground vehicles, total it's around.
But your coverage is pretty good with 6 cameras. You guys have done a good job with the setup. I think it looks quite good. So. Okay, guys. I think we are almost done with this session, right? We've went through pretty much all the items that I want to go through, and a bit more even. If you want, you can go ahead and do the joystick demo on your own time, but I think you guys have to leave at, it's 4:30 right now?
Yes.
Yeah.
It's 4:26 your time, right?
Yeah.
And you have to leave usually by 4, right?
No, it's supposed 4:30.
Today's session is 2.5 hours, Mitch. It's until.
I know it is, Raheem. I'm asking if you guys had to leave.
Yeah, they are already occupied for this session.
What's that?
They planned for this session until 4:30.
Okay, yeah. So yeah, I mean, if we could go another half an hour, it'd be good. But unfortunately, I actually have another meeting and another meeting after that. But we went through everything I want to go through. How do you guys feel so far? We got 3 minutes left.
Well, good.
Good? Yeah.
Yes.
Excellent. Okay, so we covered the architecture. You can stop this model, by the way. We covered the Q-drone hardware. We did the hardware test. We did a basic communications test. We did calibration. We defined rigid bodies, and we tested those frames of reference. You can stop your model, right?
Okay.
So, are there any other questions before we end this session? I will be sending you all the recordings of these as a package, but I'll send you to Raheem and Mr. Widodo. I can send you the recordings of the QCAR sessions from last week. I'll send you that as a package.
All right.
And if there's nothing else, gentlemen, I guess we'll start tomorrow, and we'll run the hover test.
Yes.
And do the position control application with the Q drone. I was going to take a deeper dive in the architecture, but if you want to run another kind of controller, then let me know, right? Are you guys planning on trying to do multi-vehicle stuff?
Yeah.
Yeah, possibly. Yeah.
Yeah.
Okay. Which one? You want to do the leader follower
Yeah. Leader follower. That would be fine. Leader follower.
with the Qbot 3?
Yeah.
Okay. Let me see if we have those files ready, because I don't know if they did them yet, to be honest. If not, then we have quite a bit to go through anyway. So if not, we can do it offline as well, but I don't know if they designed those files yet. Actually, I'm looking at it right now. Give me. We don't actually. We don't have for Q. You have Qbot 3, right?
Yes.
Yeah.
We don't have that yet. Unfortunately, so we can't do leader follower yet, but we can definitely talk about it in tomorrow's session, how you can get ready to set up, and I can kind of help you along the way offline as well. I'll definitely do that for you guys.
Yeah. Thank you.
But tomorrow we'll definitely we'll go through the hover test. We'll do a position control test. I want to show you a bit more of the architecture, and then we can talk about leader, follower, and swarm, and how you can go about doing that.
Okay.
All right.
Sound good?
Sounds good. Yeah.
Yeah.
Great. Have a good rest of your afternoon, and talk to you soon. And don't be shy. If you have any questions, please send me an email.
All right. Thanks.
Thank you.
Thank you.
Thank you. Bye.